హలో
నమస్తే మేడం, నేను శ్రీనివాస్ అండి.
సార్ నమస్తే సార్.
అంటే ఓకే, నిన్న like have you attended the today is what is the class? 1 minute. Are you able to hear my voice?
Yes sir.
How about video? Are you able
Yes,
to see
sir.
Okay.
Yes.
Are you present on the last classes from 5th?
Yes sir.
So today is day number 5, right? Were you present on all the 4 days?
Sir?
Were you last 4 days attend ayyara?
2 days విన్నా సార్.
Okay.
Last class విన్నా, bounded linear.
Okay. Yesterday also we had a class, though
Yes,
it was Sunday. Yesterday also there was class.
Yesterday నా సార్ నేను absent ఉన్నా సార్.
Okay, no problem.
Absent.
Okay. Now you are the only student present. Do you have any doubts to ask me?
Yesterday ఏం చెప్పారు సార్ క్లాస్ లో?
Yesterday I completed the theorem that I will write down. 1 minute, I will write down and show you. I completed this theorem. I don't remember its number. It's on page 66. 66 or 68. I will tell you. 1 minute. It's on page 66. I completed the theorem. Okay.
Okay, sir.
That is 3.4.3 theorem.
Yes, sir.
Theorem 3.4.3. Okay. This I completed on page 66. Okay. Actually, yesterday, therefore yesterday I was not able to complete. This part remained. There is the final conclusion of this theorem is that B of n dash is complete if n dash is complete. Okay. If n dash is complete, then B of n dash is complete. This I proved yesterday. Okay.
Okay, sir.
Vijaya also. You are Miss Sanjarani, right?
Yes, sir.
Okay. So today and then after this, I proved one proposition. Okay, I will write down that. That is the proposition on in the next unit. Okay, that is.
Okay.
That is 4.3.1. 4.3.1 on page 77. Okay, this 70. I proved. Let me mention, right? Let me mention this proposition. This we need to prove the next theorem. Okay, what this proposition says is the following. Let G be a proper closed subspace of a normal linear space N. Okay. Then for epsilon positive, there exists an x epsilon on the unit sphere on the unit sphere, right? Such that infimum of norm of x epsilon minus g, as that g belongs to big G, this infimum is greater than 1 minus epsilon. Okay, this I proved yesterday. I will explain this. So let me move this. Now, what this means is this. This G is a proper closed subspace of N. Okay, So we are inside a normal linear space. N is a normal linear space. In that, you have a closed subspace, G. It is a closed subspace, and also proper. Proper means what? Outside this space, there is at least one point. Okay, that's what is meant by proper, isn't it? G is a proper subset of N means there is an element in the complement of G. Outside this G, there is an element. X is an element outside G. Okay, at least one X exists. Then we say G is proper in N. Okay, and G is a closed subspace. Then, if you take any arbitrary positive epsilon, then there will be a point X epsilon on the unit sphere. Unit sphere means you have to take the circle of radius of you have to take a circle of radius 1 unit. Okay, centered at origin. This is circle of radius 1 unit. In general, it could be a sphere. So you are taking a sphere centered at origin of radius 1 unit. Okay, this is called unit sphere. On this, there will be an element, and there will be an, depending on this epsilon, there will be an element X epsilon. So there will be an element here on this circle, like on the circumference. Okay, on the surface, there will be an element X epsilon, such that if you take small g from big G, if you take any small g from big G, right? You look at the distances between these elements from X epsilon. You take this element, this distance from X, these points, as these points vary in G. This is small g. Okay, from small g to X epsilon, what is the distance? It is norm of that difference. This norm is the distance between X epsilon and G. So you let this G vary over let this small g vary over big G. So it can take any point in big, it can be any point in big G. So you'll be getting so many values. Out of all those line segments, okay, out of all the lengths of these line segments, you take infimum. That infimum will be greater than 1 minus epsilon. Okay, and because this norm is always non-negative, the infimum will be always greater than or equal to 0. Infimum of non-negative things will be greater than or equal to 0. Okay, so you want 1 minus epsilon to be greater than or equal to 0. If this is negative, that is always true. This is greater than a negative quantity. 0, right? This is non-negative. It is always greater than a negative quantity. If this is negative, there is no point. This is interesting only when this is positive. So when this happens, when epsilon is less than 1. So if when your epsilon is less than 1, this is interesting. Okay. So that's what that's what this proposition says. Okay, and this proposition is helpful in proving the next theorem, right? See, the next theorem is this theorem number 4.3.2. 4.3.2. Okay, it says if closed bonded sets are compact. Closed bounded sets are compact in a normal linear space N, then N is finite dimensional. Okay. So what this says is, what this theorem says is, you take a normal linear space, right? And in this, you take, if you have this hypothesis, this assumption that there are closed and bounded sets in this compact set, you take sets which are closed and bounded also. Okay, you take sets which are closed and bounded. If these sets are compact, and if this is true for every closed and bounded set subset of N, okay, and then this assumption makes N finite dimensional. Okay, this is the conclusion. This is the assumption, this is the conclusion. Let us see how. Well, to prove this, we'll use the previous proposition. Okay. So we'll proceed like this. So you take an element x1 in n. Usually your space should be non-trivial, then only it is interesting. So let x1 be an element in n. Okay, n is a normal linear space. So you take an element x1 in n. Okay, n is non-empty. So x1, there exists an element x1 in n. Okay. Now look at the span of this. Let x1 be the span of x1. Okay, span means you have to take all linear combinations of this. Those are scalar multiples of x1. Okay, this is also called the space generated, the vector space generated by in the proof of this theorem, this word is used. Space generated by x1. It means it is the span of x1. Okay, and then for this you take closure. For this you take closure. For the span of this you take closure. If this is n, if the closure of this span is n, then n is one dimensional. Then n is one dimensional, isn't it? If the closure of this span is equal to this space, your n becomes one dimensional because singleton x1 forms a basis for n. Okay, so the point is what happens in the when this does not happen. If this is not the case, then what happens? There exists an x2 belonging to n minus x1 span x1 closure. If this is not the case, this will be a proper subset of n. Okay, so in the complement of this, there will be an element x2. Okay, now for this you can apply for this is a closed subspace, proper subspace. X1 closure, span of x1 closure is a closed proper subspace. In the previous theorem, in the proposition, you want a G contained in n. G contained in n. So for G you can take x1 span x1 closure. That is your G now. So we apply the above proposition for G equal to span of x1 closure. Okay, this is a closed proper subspace. Okay, and you need to take an epsilon also. You need to take an epsilon. We'll take epsilon equal to half. Your epsilon is less than or equal to 1. It is interesting when your epsilon is less than or equal to 1. You take epsilon to be half. Okay, so you take epsilon to be half. Then what happens? So let me change this figure. So what we are doing, we are taking an x1 here. We are taking an x1 here. Okay, and we are collecting all scalar multiples of x1. Okay, those may be these. If this is x1, this may be 2x1, this may be 3x1, this may be 4x1, this may be minus x1, this may be minus x2. You collect all scalar multiples. Okay, and you take the closure of this set. Then it becomes this one. That is your G. Okay, and now to this and this where does this x2 lie? Your x2 lies here. Your x2 lies here. This is x2. Okay, x2 is in the complement of this span closure in n. Okay, so x2 is in n minus this closure of span of x1. Okay, this is x1. This is x1. This is x1. Right now, what does our proposition give? Proposition gives that there exists an epsilon for this epsilon. If you take elements in G, if you take elements in this, if you take elements here in this, and you take the No. Wait. How? 1 minute. There exists an x2 in there exists an x. Is it? No. Yeah. If not, there exists an x2. This is wrong. What is it? What should it be? This is on the unit sphere. There exists an x2 on the unit sphere. Okay. There exists an x2 on the unit sphere. See, what is it? Where does this x epsilon belong to? It belongs to the unit sphere. Okay, that is that I mistook. Therefore, there exists x2 on unit sphere. So, right? Unit. Right? Yeah. If not, when we apply the above proposition for this g and epsilon 2 equal to half, you take g to be this and half to be this, then this x2 will not be in the complement. I'm sorry, you correct this. Okay, this x2 will be. Let me enlarge this. This span of x1 closure. So this will be what? Yeah. This is span of. Let this be span of x1 closure. This is x1. You collect all scalar multiples of x1. Okay, and then this is your g. Okay, you take span of x1 and its closure. It is closed proper subspace of n, and then in this, right? And because this is a closed subspace, there will be 0 also, additive 0 in existing here. There will be additive 0 in this, which is additive 0 in this. Additive entity in n. So around this, you take unit sphere. Around this, you take unit sphere. Okay. So you take unit sphere around this. So on this unit sphere, okay, on this unit sphere, there will be a point x2. This is x2. Okay, x2 will be a point on the unit sphere. This radius is 1 unit. Okay, the radius of this sphere centered at 0. The identity, right, is 1. This is sphere centered at the identity of radius 1 unit, right? And on this unit sphere, there will be an element x2, right? Such that what happens? Infimum of norm of x2 minus g, such that g belongs to g is greater than 1 minus epsilon. What is 1 minus epsilon? I'm taking epsilon equal to half, so this is half. What are the elements in G? What is G? G is the span of x1 closure. This is your G. Okay, so you let small g belong to this. So to this, x1 belongs. Okay, so you have you can take x1 here. So you have norm of x2 minus x1 is greater than half. This you get. Okay. Next, if in the next step, you check whether this x2, this element x2 and x1, right? This x1 is here. X1 is in G. X1 is an element in G. This is x1. If these two elements can generate the whole of n, it's okay. Okay. X1 is an element in n, and x2 is on the unit sphere, which is subset of n. So these two are elements in n. If these two can generate n, means the if you form a basis of consisting of x1, x2, if that is basis for n, then n becomes two-dimensional. Otherwise, we work with the span of x1, x2. Okay, so we have this. if x1, x2 span, you take the span and its closure. If this is equal to n, then n is two-dimensional. Then n is two-dimensional. Okay. Now you started with x1. Okay, x1 is somewhere here. X1 is in n. If the span of x1 closure is n, then n becomes one-dimensional because singleton x1 becomes a basis. Otherwise, you take this as g. From this g, and you take by taking epsilon equal to half, you get an x2, which is not right, which is on the unit sphere. Okay, such that this is true. Norm of x2 minus x1 is greater than half. Now you consider the span of x1, x2 and its closure. If this is equal to n, then the double term x1 comma x2, this becomes a basis for n, and n becomes two-dimensional. Okay. Otherwise, you work with the complement of this. If not means if this is not equal to this, then take epsilon equal to half, and g equal to x1, x2. The span of x1, x2 closure in the above proposition. Again, the above proposition. Okay. Now I want to take the same epsilon, but my our g is varying. Previously, we took g to be a span of x1 closure. Now we'll take g to be span of x1, x2 closure. Okay. This is the base for this space. x1, x2 is a basis. Okay. And now, because g is very, because though epsilon is same, previously epsilon is half. And now also epsilon is half, but g has changed. G changed from here to this, one-dimensional to two-dimensional. It's changed. So your x3, the new element x epsilon may change. Therefore, there exists an x3 on unit sphere, in n, such that infimum of norm of x3 minus g, such that g belongs to g is greater than 1 minus epsilon, which is equal to half. Okay. I'm taking epsilon equal to half, so 1 minus epsilon is half. So, and this is right, norm of x3 minus g. Where from small g come from? Small g comes from this one. Therefore, you can take you take g equal to x1 and g equal to x. Once x1, then you take g equal to x2. So from here you get, therefore, norm of x3 minus x1 is greater than half. I'm taking g equal to x1. If I take g equal to x2, right, then norm of x2 minus x3 minus x2 is greater than half. Okay. You can take g equal to x1, then you get this. Because infimum is less than or equal to each of these values. So norm of x3 minus x1 will be greater than or equal to this. That is greater than half. So that's how this is greater than or equal to this is greater than half. So this will be greater than half. Similarly, you could take g equal to x2. So this will be greater than or equal to infimum of all these, and which is greater than half. So this will be greater than or equal to this is greater than half. Okay, this you obtain. And this now you will ask for if the span of x1, x2, x3 closure is equal to n, then n is three-dimensional. Okay, if this is the case. Otherwise, what happens? Can you tell me? Hello, friends, is there anybody?
Sir.
Yeah. If our g, if g, you take g to be the span of x1, x2, x3. Okay. If x1 comma x1 comma x2 comma x3, the span of this closure is equal, right? What did he say? Yeah. If this is equal to n, then n is n star. If it is not equal to n, what happens? If this is not equal to n, then what happens? There exists an x4 on the unit sphere such that infimum of norm of x4 minus g, as that g belongs to n, g belongs to g is greater than 1 minus half, equal to half. Okay, right? So this continues. Okay, now you can take g equal to x1 once, x2 once, x3 once. Okay, the norm of x4 minus x1 will be greater than half, norm of x2 minus x1 will norm of x4 minus x2 will be greater than half, norm of x4 minus x1 will be greater than half, norm of x4 minus x3 will be greater than half. Okay, so you are on the unit sphere, you are getting points x1 may be out, x1 may be outside. It need not be on the unit sphere, but it is non-zero. 0 is inside. Okay, x1 is non-zero, and then you have x2 here, and then some x3 here, and then some x4, and so on. Okay, you get a sequence of points x1, x2, x3, x4, and so on, x5, and so on. These points lie on the unit sphere centered at origin of radius 1. Okay, right? I did not draw properly. So let me draw properly. The sphere is not looking like sphere. So right? So you have origin here, x1 is somewhere outside, and x2 will be somewhere here, x3 will be somewhere here. And if this is not the case, there will be an x4 on the unit sphere. This radius is 1 unit. Okay. So you get a sequence of points on the unit sphere. After x4, you will get x5 and so on. These points will be lying on the unit sphere centered at origin, and the distances between any pair of them is greater than half. Okay, and this kind of sequence is not Cauchy. So continuing in this process, this way, we get a sequence x1, x2, x3, x4, and so on. Okay, lying on the unit sphere, except perhaps not x1. Okay, x1 may not lie, but all others, x2, x3, x4, all these will be lying on the unit sphere around the origin. Okay, they will lie on the unit sphere. And what kind of a sequence is this? Can it converge? If it converge, right? Can it converge? Can this sequence converge? See, every convergent sequence, every convergent sequence has to be Cauchy, but this sequence cannot be Cauchy. You have norm of x1, norm of xi minus xj is greater than half. For all I comma j, I is not equal to j. That's how you have constructed this. See, norm of x1 minus x2. If I is equal to 1, j equal to 2, this is greater than half. If 1, 2, then 1, 3, 2, 3. 1, 3 is this. This is greater than half. If the suffixes are 2, 3, this is greater than half. So out of the elements of x1, x2, x3, these are all the pairs possible. And their difference, you look at the differences, and their norms are greater than half. What happens when you get the fourth element? You have to take the differences x, right? With this new one, x1, x4. x1, x4 is one pair, right? Right? And it is great. Okay. Can you show that? or for at least these. X4, yeah. You'll get x4 minus x1 is greater than half. You can take x1 belonging to G, so x4 minus x1 will be greater than half. This distance also will be greater than half. Right? Previously you got x2 minus x1 is also greater than half. This length, and this also is greater than half. So let me use a different color. This distance is greater than half. This distance is greater than half. This is greater than half. This is greater than half. Okay, so these elements will not be forming a Cauchy sequence. Okay, because of these inequalities, right? If you call this one and this one is 2, okay, and then yeah, because of this 3, right? 1, 2, 3. This imply that this sequence xi is I equal to 1 to infinity is not Cauchy. Okay. So a convergent sequence, a sequence is convergent. Okay. A convergent sequence has to be Cauchy. So if you have a non-Cauchy sequence, okay, will not be convergent. Okay. So you will have x1, x2, x3, x4, and so on. This is not convergent. Okay, the sequence is not convergent, and so on is not convergent. Right. So you are able to produce a sequence x1, x2, x3, x4, x5, and so on, which is not convergent. And yeah, you can leave x1. Right, one term you can leave. The initial term you can leave, but you can leave the first term, but remaining terms, for the remaining terms, they are lying on the closed unit sphere, right? It is what is this? This is norm. This sphere is what? This is norm. The set of points for which set y that norm y equal to 1. Okay, this is closed. These are points coming from N. Okay, this is closed, right? Norm is continuous function, right? Therefore, this inverse image of the singleton one is closed, so this will be closed, and it is bounded also. It is bounded by 1. Okay, therefore, this is a closed and bounded set, but it is not compact. Our assumption is that every closed and bounded set is compact. Every closed and bounded set is compact. Okay, but here we are able. So yeah. So we are able to get a compact set. In that set, we are able to get a sequence of points x2, x3, x4, and so on. And the sequence on unit sphere, right? And because unit sphere is compact, why? It is closed and bounded. Unit sphere is closed and bounded. Unit sphere is closed and bounded. So by hypothesis, it is compact. Okay. Unit sphere is closed and bounded, and by hypothesis, it is compact. By hypothesis, right? Hypothesis may what is hypothesis? Every closed and bounded set is compact. Therefore, this has to be compact. So on this compact set, we are able to get a sequence which is not convergent. And right, we are inside a normal linear space. We are inside a normal linear space. We are inside a normal linear space. N is normal linear space. Unit sphere lies on N. Okay, G lies on N. So we are inside a normal linear space. In that, the compactness is equivalent to sequential compactness. So every sequence must have a convergent subsequence. If a sequence is not convergent, it cannot have a convergent subsequence. Okay, so that's how, right? Okay, we get a contradiction. Okay? Because of this, right? Because of this, if you call this some 5, so but 5 contradicts. Okay, 5 contradicts. Okay, out of this set, we are able to produce a sequence which is not convergent. Okay, yeah, right? Therefore, Therefore, this set is not. Therefore, what is our what happens? Somewhere it has to stop, right? Right? This property. You see. First, we took G to be one-dimensional, and then we took G to be two-dimensional, and then we went G to be three-dimensional. Right? This process cannot be continued indefinitely. If that is the case, we end up with a sequence which is not convergent. Okay, right? Okay, right? So what happens? That is why this process has to stop somewhere. Means n will be equal to this. After a finite suffix, the closure of this span of finite number of elements must be n. Means your n becomes finite dimensional. Okay. Therefore, there exists an n naught such that span of x1, x2, x3, and so on up to xn naught closure. This will be equal to n. Right. Therefore, n is finite dimensional. N is finite dimensional. Okay. Here, in this, so 1 minute. Let me see here. What in the book he's saying? Would obtain a sequence of points on the unit sphere which has no convergent subsequence. Yeah. He says this sequence has no convergent subsequence. Okay. This sequence has no convergent subsequence. Why? Because the sequence is not Cauchy. Yeah. This sequence cannot have a convergent subsequence. Yes. This sequence cannot have a convergent subsequence. Let me mention. Convergent subsequence. Okay. Not convergent. Why? I should not say not convergent. Okay. This is not Cauchy. Not Cauchy implies this is okay. Yeah. Here I should change a little. I will change the argument like this. This sequence, therefore, this is not convergent. This sequence x2, x3, x4 cannot have a convergent subsequence. What happens? It has a convergent subsequence. That convergent subsequence will be becoming Cauchy. But we showed that this sequence is not Cauchy because of this. Okay, norm of x2 minus x1 is greater than half. Norm of x2 minus x3 minus x1 is greater than half. x3 minus x2 is greater than half. Norm of these things. Okay, this x4 minus x1, x4 minus x2, x4 minus x3, all these greater than half. So because of this, no convergent subsequence of this, no sequence of this sequence, no subsequence of this sequence can be convergent. Means no convergent subsequence exists for this sequence. Okay, so this sequence cannot have a convergent subsequence. Hence, it is not convergent. From here, you have to say. From here, you can say it is not convergent. Okay, from here you can say the sequence is not convergent. Okay, because this does not have any convergent sequence. This sequence will not be convergent. Then it's correct. Okay, so this process cannot go indefinitely. So it has to terminate at a finite for a finite suffix. Okay, that's how your n becomes finite dimensional. Okay, so that is the use of this proposition, right? You have to remember this proposition in the exam. You may be asked to show that if closest bounded subsets are compact in a normal linear space, then show that n is finite dimensional. If you're asked like that, you have to write down the proposition. You have to write down the statement of this proposition. You have to remember the statement of this proposition, write down, and then using that proposition, you may go for this. You may go to prove this theorem. Okay, that's how we show that if closed and bounded sets are compact in a normal linear space, then that normal linear space has to be finite dimensional. Okay, then you have a corollary for this theorem. Let me discuss that. Corollary, right? Yeah. What is this? What does the corollary say? let n be a normal linear space, and suppose S equal to x belonging to n, so the norm x equal to 1 is compact, and n is finite dimensional. Okay, let n be a normal linear space. Corollary 4.3.3. Corollary 4.3.3. Let n be a normal linear space and S be equal to x belonging to n, such that norm x is equal to 1. Okay. This is the unit sphere centered at origin of radius 1. Okay. This is the unit sphere in this normal linear space. The unit sphere, this is the radius of this circle. This is a sphere. Okay. This is the radius. 1 is the radius. And let this be compact. Okay. Let this and this be compact. Then n is finite dimensional. Finite dimensional means what? When do you say a vector space is finite dimensional? When its basis has finite number of elements. When the basis of a vector space has finite number of elements, then we say that vector space is finite dimensional. Okay. How can we prove? So let A be a subset of n. Let A be a subset of n. be closed and bounded. Okay. Right. We'll try to show. We want to apply this theorem. So right. So we are given a normal linear space, and in that we take an arbitrary closed and bounded set. We try to show that it is compact. Then n becomes finite dimensional. Okay. So that's what we are trying for. So we are given a normal linear space. In that you take an arbitrary set which is closed and bound. Okay. Right. From boundedness, what do you get? There exists an r greater than 0 such that this bound, right? Such that A is contained in the closed bond centered at 0 of radius r. Okay. Why? That's what we mean by boundedness. What is boundedness? See, we are inside a normal linear space, right? And where A is, this is capital A, and this is bounded means what? The origin as center, you can find a closed sphere of radius r. Okay. You take origin. Okay. This is origin, right? And a positive radius. Around this, you take a circle of positive radius, right? So inside that circle, inside that circle, okay. Now you assume this is a sphere. The red one is a sphere. So the radius of this is a small r. Okay. This is small a. This is small a. This is big A. Right? A will be a subset of this open sphere. This closed sphere. Okay. This closed sphere. This is B of 0 r. Okay. This can also be written as SR of 0. Like that you can write. Okay. Now what happens? Now is this is a closed linear sphere B of 0 r. What is this? How can we write this? B of 0 r is equal to x belonging to n such that norm x is less than or equal to r. By B of 0 r, we mean this. You have to take less than or equal to. Okay, and this is closed and bounded. This is a closed set, and it is bounded also, right? A closed sphere is bounded. Okay, so and if your r is less than 1, so this will be subset of S. This is contained in S. If your R is less than 1, then this will be subset of S. Okay, and SA is compact, and this becomes a closed subset of S. So closed subset of a compact set is compact, right? Closed subset. Yeah. Let me. So let me put this in words. B of 0R is closed and bounded, right? Closed and bounded. Closed and bounded. Closed and bounded. Okay, and yeah, we are assuming S is compact. Therefore, in fact, we don't need this because your S is compact. Your A is contained in this. This is contained in S because S is compact. This is compact by assumption. By assumption, this is compact. Okay, so and your A is closed. We assume that A is closed. So your A will be a closed subset of a compact set. So it will be compact. So that's how you can conclude. Okay. Yeah. Therefore, yeah. And A is closed and contained. A is closed and contained in compact set S and compact S. Therefore, A is compact. Okay. Okay, closest subset of a compact set is compact. That's how A is compact. So you are able to show that A is compact. A is compact. So you started with a closed and bounded set, and you are able to show that A is compact. Therefore, by the theorem, what does theorem say? If in a normal linear space, closed and bounded sets are compact, that normal linear space has to be finite dimensional. So theorem says by theorem, right? The theorem implies that N is finite dimensional. N is finite dimensional. Okay. In this, I have a doubt. If your R is less than 1, it is okay. If your R is less than 1, then B will be contained in S. It is okay. But if your R is greater than or equal to 1, if your R is strictly greater than 1, then what happens? Then I'm not convinced when R is greater than 1. Okay, I meant to verify that part. When your R is less than 1, this is correct. In your book also, it's not done. What happened? Why? No upper bound on R is discussed. I doubt whether R can be greater than 1. Okay, so that I will sort out later. Right? If your R is less than 1, then definitely this B of 0R is contained in S, and A becomes compact. Then you don't have any problem. So the question is to settle down if R is not greater than 1. Okay. The question is to assert that R cannot be greater than 1. Okay. That no, I cannot do. I don't have reason. Later on, I will clear that. Okay. So this is what the corollary says. Okay. And then we'll enter the next topic. What is the time now? 02. So how many people are there? So it is the same people, Sancharani, Bhanu Prasad ji, or Teja. Teja is a boy or a girl? Patnam Teja.
Yes,
Madam. It is madam. Yeah. So you people are the most regular. Other people might be busy with some job, something like that. Okay. So shall I stop here? What do you want me to do now? Hello? Can I stop? Shall I stop here? I think you will. Minds are heated up so much.
Yes, sir.
Since morning, you people are, bombarded with mathematics.
Continuously, sir.
Yeah. I don't know. By the end of these 16 days, what happens to your brains? I don't know.
We are not even given a small break for lunch, sir.
Yeah. Okay. So, at what time you want that you tell me? When will it be okay? At what time you want, Bhanu Prasad ji?
Okay, sir.
Lunch at 2 o'clock. of 1:30, 2:30. At 2:30, shall I ask them to wind up? At 2:30?
2:30 to at least 15 minutes lunch time they break. That is better, sir.
Maybe I'll ask right at 12:30 to 1:30, and then maybe between 1:30 and 2:30. Okay.
Yes, sir.
They will give you some 20 minutes time like that. At 1:30, they may wind up by 1:20 like that, and the other one may wind up by short, some 15 minutes late. Okay. I will ask those teachers to leave you a bit early. Okay, for lunch. Okay, right? Definitely, we'll do that. So today I want to stop here. I don't want to continue because the students are not many, and then only 2 students are there, right? I don't want to continue anymore, right? Okay, I will stop. Is it okay, or you want me to ask something? Hello. Okay, I'm stopping here.
Sir?